Hey everyone, we've got just one more stats lecture, one more thing to talk about. Let's get right to it. Hoping for a pretty short video here because our last topic I think is a pretty straightforward one. Keep in mind we're looking at quantitative data. And we're asking the big question, are these things correlated? Are these two variables correlated where both of my variables are quantitative in nature? We've done a lot with proportions, we've done a lot with categorical, but now we're looking at observational units that have two quantitative variables, and we want to see if those have a connection. We've done a lot in terms of terminology. We've talked about the correlation coefficient, we've talked about the regression lines, and R squared and the things of measuring that. But up until now, we have not developed a way of answering the question, how do we show that there's statistical significance here? How do I argue that there actually is correlation? And so to talk about how we make that argument, let me give you just a short example here. Here is the situation that I have concocted. Do older people like slower music? That's the research question that we're going with. So here's the again fictional situation. I had 250 people listen to 50 songs across various genres, which is already super impressive that I got 250 people to listen to 50 different songs each. They all listened to the same 50 songs. Everyone told me their top. I'm not even going to delete that in editing. Everyone told me their top 5 favorite songs, and then I kept track of the beats per minute of each song and took the average for each person. Again, this is fictional, but I think I really want to do this one. This one, I'm very, very curious actually to see how this would play out. I just have to find 250 people who will listen to 50 songs each. So okay, so we do that. We gather the data, and what I get here is 2 quantitative variables for each person, right? I've got that person's age and the average beats per minute of their top 5 favorite songs. And I want to see, are these correlated? As age goes up, does beats per minute go down? Now that's the research question here. But probably I should do it two-sided just to be on the safe side, right? And make sure that it isn't potentially correlated in the other way, right? Maybe older people prefer faster music, and we just haven't really considered that possibility. I know I haven't. But what would this look like? How do we make an argument here? Well, here's the data, and it looks pretty convincingly like it has a negative slope. Again, I remind you, this is fictional, not fact. I did not actually gather this data. But let's talk about this in terms of statistics the way that we always have. Our null hypothesis here is that there is no correlation. There is no connection between the two things. That anything we see is just random chance. The fancy math notation that we'll have here is we'll use the Greek letter beta. Beta represents the slope of the regression line. So the slope of this line, of the true line of best fit for all people everywhere, not just our sample. Our null hypothesis says that the slope of that line for the whole population is 0. And that if you got anything else, then that was luck. Okay, the alternate hypothesis would be that there is some correlation, that in other words that the slope of that line is not 0, whether it's positive or negative or what have you. If we went by the legit version of my research question, I would probably say that beta is less than 0 if I'm feeling pretty confident that older people like slower music, that the slope of that line then would be negative. And looking at my data, I got strong suspicion to believe that that's true. But now how do I argue that, right? The whole goal of statistics here is to say, if the null hypothesis is true, then what are the chances that I would get what I got? How do I bring randomness into this? Because the null hypothesis is all about randomness, random chance, that I got what I got because I got lucky, because it just happened to be that way. Well, here's what randomness would look like in this scenario. All of my data is made up of these ordered pairs, right? I've got, this person, age 70, average beats per minute of their favorite songs, 45, right? This person, 59 years old, on average, 81 beats per minute their favorite songs. This person, 20 years old, apparently listens to a lot of electronica, and 196 was the average. Jeez, okay. Now, if this was my data, and this is what gives me this picture, and this slope, and this regression line, the null hypothesis says, hey, you got that by luck. There's not actually any association here between these two things. Okay, well, if that's true, then it shouldn't matter which y values in these points go with which x values. That's how we can bring randomness into this. We can say if it really doesn't matter, and I'm just as likely to get, then I would be just as likely to have had this 45 be with the 20-year-old. And to have this 196 be with a 67-year-old, right? If everything is truly random and I just happen to get this selection of people, then the y values aren't connected to those x values in any way. So I could just take them all, shuffle them up, scramble them up, and then send them back over and create these new points. And I can look at the new scatteredness of all of them and all of the points that I would get and find the regression line of that collection of data. And then look at the slope, right? All we're doing here is looking at slope. That is the statistic that we're keeping track of when we shuffle things up 10,000 times. Because ultimately the question that we're trying to answer here, what are the chances that I get what I got? The thing that I got that I'm examining is the slope of that regression line, that line of best fit. What are the chances that I would get a slope as extreme as the one that I did? If the null hypothesis is true, these don't connect to these, so I can shuffle them all up. 10,000 times I'll shuffle them all up and look at the slope of that regression line. And it should be centered at 0, as the null hypothesis says. And I get some data that looks like this. Then I could, count them up out of the 10,000 times, or in this case it was 10,001. The 10,001 times that I did this, how often or how many times did I get a slope as extreme as the one that I saw? The regression line in the picture you just saw had a slope of like -2 point something. And nothing here even comes close. If you run this simulation and ask for the p-value, how many times did I get a slope beyond -2 point something? It's a hard 0, not even close. It shrinks the whole graph when it draws the lines. Gives pretty strong evidence that if the null hypothesis is true and there is no correlation, then it's pretty unlikely that I would get what I got. On the flip side, here's some data where it is close, so close that we actually don't get to reject the null hypothesis. This is from the correlation regression applet, and I picked one of the standard ones, the data exercise mood, which I guess is looking at any correlation between the intensity of exercise and the change of one's mood. I'd be intrigued to see how they measured either of those things, but alas, here we are. When you select that data and hit use data, it shows you this. Now there's only 32 points, so there's not a whole lot of data to work with here. The regression line is given by this, so we can see kind of the statistic that we're looking at, the 0.1368. And here I did it again. I checked the shuffle options. I only did 1,000 instead of 10,000 because it was actually taking the computer a little bit of time to do it. Probably because it's drawing all of these regression lines, which I guess takes memory. Who knew? And then plots them all out, all of the different slopes that we get. Now, the slope of the regression line that we got in our data was this, 0.1368. So I checked how many times we got a slope that was at least as big as that, in either direction, positive or negative, and it turned out to be kind of a lot. 32.10% of the time we got a slope that was at least that big, and that's not small enough, right? This p-value is bigger than 0.05, so we will fail to reject the null hypothesis there. So this is great. We've got randomness, we've got a simulation, we've got a p-value, we've got everything that we need. The only other thing that we would want is a theoretical approach. How could we answer this question without having to simulate 10,000 times? Which in this case is actually feels even more relevant because my computer was kind of, huffing and puffing there at the end when I was trying to simulate 10,000 times. It took it a minute to think about that. And we want to be able to do this. In general, most of the time when we're doing statistics, we're usually doing a theoretical approach. Anytime we're doing a theoretical approach, we have the same kinds of questions, but the main one that we've been wrestling with throughout Unit 3 is just, what statistic should we use? We want a statistic that's going to give us a distribution that we actually know and understand and can use mathematically to get p-values or standardized statistics or what have you. So how do we do that here? What statistic are we going to look at? Using the slope by itself, we don't exactly get a nice distribution that we know everything about. So that one doesn't quite work. Even looking at some other things like R squared, correlation coefficients, we just don't know about the distribution that's going to come from that. But we do have a statistic that will do the job. The statistic that we want is another t-statistic that gives us another t-distribution, not a standardized thing here. There's actually a couple of ways to find it. I think one of the interesting ways to do it is actually to use that r value, that correlation coefficient, and then we standardize it with the whole square root of 1 minus r squared over n minus 2. That's one way to get the statistic. The other way is actually to use the slopes of the regression lines, b being the slope of the regression line that you get, and then standardizing it with the standard error of the slopes, which we have not talked about what that standard error is or how to find it, and I have no intention of doing so because we're never going to do that by hand. I'm mentioning these calculations rather in passing because we're just going to rely on the applets to find them for us. But this is great. This gives us a statistic that we can look at and then draw statistical conclusions without ever actually having to simulate. In the case of our exercise data, if you wanted to see a picture of it, you would want to change your statistic. It's up here. I think it's up here. You'd have to scroll up to see it, but this is just a picture. I can't scroll up. To change it to a t-statistic. And then in order to see what your t-statistic is, you'd actually have to check a thing down here for the regression table. I'll show you that in a moment. But checking the overlay t-distribution will show you the distribution that we get from finding that theoretically, and the theory-based p-value that comes from it. This theory-based p-value is enormous, just like the simulation one is, so we should fail to reject. With my data from earlier, it's quite on the other end. Here, checking this regression table shows this whole table here, and it's this line down here that gives us all the pieces that we're interested in. That t-statistic that's being compared, and the relevant p-value, which here is just astronomically small, so I wouldn't have any doubts about rejecting the null hypothesis here. What I want to point out is that what's nice about this theoretical approach is that I don't need to do any simulation. I didn't even check the box for show the options. Checking this table shows me that t-statistic, and more importantly, just straight up hands me the p-value, that theoretical p-value, and I can draw my conclusions immediately. How glorious is this? It's just Control V to paste my data in, use data, and then check this box, and voila, the computer does all of the math for me and gives me a theoretical p-value that I can rely on. So we're back in this feeling that I talked about when I took statistics of just, I take my data, I give it to the computer and say, please to stats, and it gives me the things back. And it's a good gig. It's the computing power has really changed the way that we think about statistics in general. And it's a really powerful tool. This applet isn't the only one that can do this. Most statistical packages, and by most I mean all, should be able to do this kind of computation for you. And that's what a lot of it looks like. Hand it the data, it gives you a theoretical p-value, and that's what we go off. There's just a few important things that I want to mention here as we wrap this up. A few important notes. First of all, I want to mention that this is only about whether there is correlation, not how big the correlation is. I mean, it's possible that there's a correlation between two things, but it's a very, very small one. In which case, the slope of your regression line might be like 0.04 or something like that, which is just really, really small. But when we're testing that, theoretically or by simulation, we're just looking at, hey, out of all of the data here, what are the chances that I would get a slope that big? It doesn't matter how big that slope is. If it's hard to get that slope, then we're going to come back with a small p-value and reject the null hypothesis. So just because we reject the null hypothesis and say, yes, we believe there is correlation, it doesn't mean that it's a big correlation. It doesn't mean that it's a strong correlation. It might be just barely a positive or barely a negative slope, so that, yeah, there's correlation, but it's not real impressive. There are validity conditions too, and with any theoretical approach, we need to make sure that those are met. Whether we want to draw conclusions about the statistical significance, or if we ever want to use like confidence intervals or anything. The validity conditions here are threefold. First, it needs to be linear. It needs to appear to at least have a linear trend. Second, you want to make sure you've got about the same number of points above your regression line and below the regression line, that there's a balance there. If you've got just like a few points that are, like really high or really low and they're dragging the line up, then that's an indication that, yeah, you probably shouldn't be using a theoretical approach here. And then finally, equal variance across the x-axis. In other words, you don't want all of your data kind of clumped in one area when it comes to your explanatory variable. If you look at my graphs there, all of the data is equally spread horizontally. I don't have any outliers when it comes to my explanatory variable. Things should be equally spread out along the x-axis, and that's our last validity condition. Last thing I want to mention here is that, again, things might be more meaningful if we're able to split into categories. And so in the previous sections, we looked at maybe taking our data and saying, hey, are there any categories, any groups I can put these in that are going to potentially give me more explanation here? And if we're able to do that, that's great. The more information, the better. And we might actually change our p-value significantly if we focus on one group. I've got to try it with a buddy here. Of course, you don't have a buddy near you, or maybe you do, in which case, go for it. But go ahead and give this question a whirl on your own. I created a Devereaux adulting metric to measure how adult someone is. It measures things like what time you go to bed, whether you have a favorite spatula, and how strong your preferences are on how green beans should be cooked. I'd like my metric scores to actually be correlated with age, so that bigger values of my metric correspond with a larger age, a higher age. The data is all up on Moodle under age metric. Is there a statistically significant correlation? So under the exploration folder on Moodle, copy that and take a theoretical approach and see if you can get any statistical significance. Pause the video here to give it a try, and I'll show you what I got in a moment. Here's what I got. when I put the data in, it looks pretty scattered. Looks pretty scattered up here, but my regression table shows me that the p-value is in fact less than 0.05. So I do have strong evidence that there actually is a correlation, giving me some confidence that, yeah, it looks like as age goes up, so does my Devereaux adulting metric as well. And that's it. That is our last section of stats that we're going to cover. Please let me know if you guys have any questions about this section or if you want to chat about it some more. Remember, final presentations start this Wednesday, and I'm really looking forward to seeing what you all came up with. Let me know if you need me, and take care.